Dear students, welcome back to the SLMC 13 hard questions. So here the hard question means it's not like really hard, so take in time, but you need more observation skills to solve this problem. So if you observe the correct approach, then it's a matter of time. Then it's like few minutes you have to spend to solve this problem. And these hard set of hard questions, you may need uh, some theorems, but like not the hard theorems, the theorems you know from your advanced level, and also some modular arithmetic. So let us go for the first question. Okay, the first question is, the function is defined recursively. F1, F2 equals 1, and Fn is the uh, equal to Fn minus 1 minus Fn minus 2 plus n for all integers n greater than or equal to 3. What is F2020? So when you look at the answers, this is one way. You look at the answers and get to know about the properties of this function. You can see these answers are not so different to 2020. That means this function should be a linear function. That means this function, the value should be closer to n, something closer to n. So since we know that, and that is one thing. This is f closer to n. And second thing is, since we know that this we need to find 20 f2020, if you are going to, like, there can be two ways. Like, either find a formula, find a closed form formula to this function. So you can solve the recursion, you may try to solve the recursion and find like Fn equals like an plus b, something like that. So this is one approach, but we don't know whether we can actually find the closed form formula. We don't know. And second thing is, you can find a repetitive relationship. That means like you can find whether this is periodic. Like you can see, you can try to write f1, f2, and so on, and you may find after some time this function gets repeated. That means again, like if this is f10 may be equal to f1. So it's something like a sine curve. So you will see that same set of function values are repeated. So by looking at this, the best way, like it will not take much time. The best way is to just try with different values of this function to see whether there's a repetition, whether this is periodic. But again, when you see this function, you have this part of n. Yeah, this part of n. So if you write, if you are like just, this is just like not writing, but trying to understand the question. If you are going to write these function values in terms of n, you can see that the periodicity, like this is not really periodic. So that is what you are going to observe when you write f1 equals 1, f2 equals 1, f3 equals 3, and so on. Like when you write few number of terms, you will see that this is not periodic. It's not periodic, but still we don't we can still have hope. So one thing we can do is we can absorb this n into the other function values, because it is the value of n that makes this non-periodic, and what we can do is absorb n. So to absorb n, you can write something like this. F n minus n. So that means you have taken the right side n to the left side, and now you need to balance this fn minus 1. So let's put n here because we know that n gets cancelled out, but this n should be parameterized by n minus 1. So it's n minus 1 minus fn minus 1 minus, sorry, fn minus 2 minus n minus 2. And now let's see what happens when you simplify this. You have another another 1, 2 minus 2, 1. 1 minus 2 is minus 1. So you can see there's a minus 1 additional. So this minus 1 can be balanced by this by a plus 1. And now you can take this plus 1 to the left side, and you can add the same constant number to both of these parts of the formula. Now can you see there's a pattern, and this n is absorbed, and the resulting constant terms after absorbing n are also absorbed. Now we can substitute this part by different function gn. And we can also now we have a simpler function where we would see a repetition because there's no end, and there is this subtraction because if it is addition, there's no repetition, it just adds up exponentially. But since this is subtraction, chances are high that this will be periodic. Now let's check how this becomes periodic. So let's start with G1. So G1, we don't need the period, this recursive definition, else we will use G1 equals F1 minus 1 F1 minus 1 minus 1. So F1 is 1, minus 2 equals minus 1. G1 is minus 1. G2 similarly, F2 minus 2 minus 1, 1 minus 3 equals minus 2. So now you know G1 and G2, the values of G1 and G2. But let's find the other values as well, but without substituting to G1 and G2, because if we have just G1 and G2, we will be able to see a pattern in terms of G1 and G2. Now let's see what is G3. G3 is G2 minus G1, and G4 is G3 minus G2. That means G2 minus G1 minus G2 minus G1. And G5, G4 minus G3 equals to minus G2. G6 minus G1 minus G2 equals G2 minus G1. Okay, now we are getting there. G7 Sorry, I did some mistake. For G6, it should be G1 minus G2, and G7 would be G1, and G8 would be G2. Now you can see this is repeated. So first two terms appear again, and now we can see it's a periodic function of period 6. So each 6 terms repeats. Okay. Now what we can do, it's very straightforward. You find G 2020 and then deduce F 2020. So you know that this has a period of 6. That means we have to find 2020 mod 6. That means until so it becomes 2016 plus 4. So until 2016, it's a multiple of 6. That means 2016 term is G1 minus G2, and then we have to consider 4 other terms, so it becomes minus G1. So let's substitute. Let's substitute minus G1. So we know that F 2020 equals N G 2020 plus N plus 1. G 2020, we know that is mod 4 minus G1 minus G1. N is 2020 plus 1. We know that G1 is minus 1 from here. So minus 1 is plus 1. 2022. Even though it took time for me to explain, like when you observe this, it's just a matter of few seconds. Sorry, few minutes. But something to be noted is these are hard questions, and if you try this and select the wrong answer, you will get 0 marks. So, and you know that these are tricky questions, so you may miss some boundary case and you lose all the marks for your effort. So the best way is to verify your answer and be very confident about your answer and choose that answer. Because like if you do all 10 and you miss marks due to some uh, due to missing boundary cases, it will be 0. But if you leave up some of the questions, then still you will receive some marks that will add up to your final score, which will increase your chances of getting selected to the second round. So please consider that as well. Okay. Question 22 is about, this is something you are familiar with, the polynomials and the roots and sum of roots, product of roots. So you should be familiar if you are doing advanced level mathematics. So let's see how this works. Here the difference is this is a fourth order polynomial. So so this is the question, and you can see some key point: positive integers. So when you work in advanced level, it's about real numbers, but here they say that the roots are positive integers. So we have to use the theorems between integers, the properties of the integers, or positive integers. Now you are asked about Q, and let's use some properties of the polynomial roots. So -7. So if you remember your quadratic equation, you say x squared plus bx plus c equals 0. The sum of the roots is minus b over a. You know that. So similarly, in this polynomial also, you can prove it. You can prove it by representing them as a product of linear terms, like z minus alpha into z minus beta, so on. You can prove that minus b over a equals the sum of roots. So let's say it's alpha, beta, gamma, and delta. So this means minus b is 7. That means this is 7. So you have one equation. So similarly, I'm not going to prove those parts. These things can be derived by using the expansion, using the above expansion, and then Q. So you can see that Q equals the summation of products of two roots. So all the combination, like, so you have 4 roots, so you choose any two and sum them. So that means you will get alpha beta plus alpha gamma plus alpha delta plus beta gamma plus beta delta plus gamma delta. You can verify whether you have considered all the combinations. You know that there are 4 and you have to choose 2. So 4C2. 4C2 is 6. So you have 6 terms. So this is Q. And this is what you have to find. And what is the other equation? So easily you can have the equation for the product. So alpha, beta, gamma, delta equals, I have to check whether it's plus or minus 6. So this becomes minus b. This is plus, minus, plus. Okay, should be plus. Yeah, it should be plus because there are 4 terms, 4 minus terms. So when they are multiplied together, that becomes plus. So alpha, beta, gamma, delta product equals to 6. Okay. Now, if this was a real equation from the real numbers, this is not so straightforward to solve. But since these are positive integers, we can check the possible values for alpha, beta, gamma, delta. So since they are positive integers, alpha, beta, gamma, delta should be factors of 6. So there can be 2 ways that you can write factors of 6. It can be 2, 3, 1, 1, or it can be 1, 1, 1, 6. So these are the 2 ways that you can write 6 as a product of its factors. Like there are, when you consider the factors, like 2 and 3 are factors and 6 is a factor, and the other positions can be filled by using 1. Now, so these are 2 different combinations, and you need to check what is the valid combination. In the valid combination, the summation of alpha, beta, gamma, delta should be equal to 7. And you can see in this case, the summation equals to 9. Which says that it's not the not the possible set of alpha, beta, gamma, delta. So it should be 2, 3, 1, 1. So now you know the combination of the values, but you don't know what exactly are alpha, beta, gamma, delta, but you know the combination of values. Again, you don't have to know the exact values because these are taken without loss of generality. So these are the combination. So since we know the combination, you have to evaluate Q. So evaluating Q is just taking any two values. So you take 2 into 3 plus 2 into 1 plus 2 into 1 plus, again start from 3 into 1 plus 3 into 1 plus 1 into 1. Just sum them up. 6 plus 2 plus 2 plus 3 plus 1. 10, 16, 17. The answer is 17. So this is something you can do by applying your knowledge about uh, the roots of polynomials, and also applying your knowledge about positive integers. Hope this is clear. Okay, so question 23. So here we need to consider three statements and the sequence 1, 11, 111. Okay, so let's see the first statement. The sequence contains infinitely many perfect squares. So if you remember, in the first set of questions also, we have used some properties of the perfect squares. So since we have this kind of sequence, it's best to start with the modulo properties of perfect squares. So we can check whether the modulo properties of the perfect squares are present in this particular sequence. So for example, let's have the modulo 4. We can try modulo 4 since that is what we know. So if you remember, you can say that any odd perfect square is 4k plus 1. Any odd perfect square, and you can see all these numbers in this sequence are odd numbers. And if there is a perfect square within this sequence, that number should be in the form of 4k plus 1. Now let's see whether there is any number in the form of 4k plus 1. But what can you say about like the first value? Yes, first value is 4k plus 1. So, and 1 is a perfect square. So this is perfectly fine. But what do you say? The statement says that it contains infinitely many perfect squares. Infinitely many. So if we find the last perfect square in the sequence, and we can say that after that we don't have any perfect squares. Now let's see. So we know that 1 is a perfect square. But after that, can you see that any other number in the sequence except 1 are in the form of 4k plus 1? Now can you see the property? Each number ends with 11. Each number except 1 ends with 11. And if you remember how you find the mod 4, how you find mod 4, you can see always the last two digits, the modulo of the last two digits, mod 4 of the last two digits is mod 4 of the number. Y, digits after last two digits, is a multiple of 100, which is a multiple of 4. So any number can be written as a multiple, like any number greater than 100 can be written as a summation of multiple of 100 plus the last two digits. So the mod 4 of this number is just the mod 4 of last two digits. Right. Now we know that. And we also know that in this sequence, always the last two digits are 11. Like after the first term, all the numbers have last two digits as 11. So what is left to find is the modulo 4 of 11. Okay. Apparently, 11 is 3 mod 4. Or this is in the form of 4k plus 3. And 4k plus 3 can never be a perfect square. So that means any term in the sequence that is ending with 11 cannot be a perfect square. That means none of them can be perfect squares. So only one is a perfect square. So the statement that the sequence contains infinitely many perfect squares is not correct. Okay. Now let's see about second and third statements. Here I'm going to start with third, because if we prove the third, it indirectly proves the second one also, because third is about natural number and second is about prime number. So if something is correct for something holds for all the natural numbers, it would hold for prime numbers as well. But actually we don't know whether this is true or not, but we need to find. So what is said here is if n is a natural number not divisible by 2 or 5. 2 or 5. So this gives some hint. 2 or 5. Because if you observe correctly, the difference between any two terms is divisible by 10, and 2 and 5 are factors of 10. So these are just observations, like not directly mapping them to the question, but you can actually just observe like 2 and 5 are there, and 2 and 5, like they if a number is divisible by 2 and 5, that means number is divisible by 10. You can also observe that the difference between any two terms is a multiple of 10. So multiple of 10. So what is said is, for any natural number, there is a multiple of n. But what you can see is, you can consider those numbers, some of these numbers, which are specified by this statement. For example, you can consider 3, you can consider 7, you can consider 9, 11, anything. If you check just some values, always see that there is a multiple. For example, for 3, 111 is a multiple of 3. And 9 you can easily find, like 9 months, and 11 you have, and 7 also uh, there should be if you like find, you can see that whatever the number you choose, there is like that number divides some number in the sequence. So if that is the case, then it is left to prove that this happens. That means it is inevitable that there is a number which is divisible by the natural number n. So we are trying out something here. Let's say that we choose any n plus 1 numbers from the sequence, any n plus 1, and you know that there are only n modulo classes, mod n. Why we are considering mod n? Because we are trying to find the divisibility. So if we are trying to find the divisibility, we need to consider all the modulo classes, and we need to find there's a number with modulo 0. And what we are going to find is we consider all the modulo classes of n, 0 to n, 0, 1, 2, 3, 4 to n. And you should be able to see that when there are n modulo classes and when you choose n plus 1 numbers by pigeonhole principle, you can find a modulo class where two numbers are repeated by pigeonhole principle. There is a modulo class where two numbers in the sequence have same value. Means you can find two numbers in the same modulo class. Two numbers in the same modulo class. Two numbers in same modulo class. So let's say these two numbers. So let's say what is the sequence A? Let's say the sequence is AN. So we have AN1 equals M mod N, and AN2 also M mod N. Okay, but now you should observe something. So when you have two M's and when you subtract one from another, you will arrive at 0 mod N. So this is an observation. So you have arrived at a multiple of n by using these two sequence values. And I also reminded you that subtracting any two values in the sequence will make a multiple of 10. So that means if an is, like, let's say we have n1 number of ones and here n2 number of ones. And without loss of generally, let's say that an1 is the larger one, so n1 is greater than n2. That means you will find n2 number of zeros, n2 zeros, and n1 minus n2 ones. And now you can see this is a multiple of 10. So this means you can write this number as 10 into some capital M into a n1 minus n2, which is a member of the sequence. You know that this is 0 mod n, right? Now there's only one step to be done. You know that n is not a multiple of 2 or 5. That means n is not a multiple of 10. So when n is not a multiple of 10, when n is not a multiple of 10, this means the sequence value should be a multiple of 10. Sorry, multiple of n. So since n is not a multiple of 10, this whole number, like if n is a multiple of 10, that means this 10 and n has common factors, and when we remove the common factors, a n1 minus n2 may not necessarily be a multiple of n. But since 10 and n are independent, the factors of n are completely present in this. And this is actually not 10 into m. So this I have to emphasize that fact also. This is not just simple multiple of 10. This is 10 to the power. This is 10 to the power n2. This means it is just 2 to the power n2 into 5 to the power n2. So there are no other factors. So if n does not have 2 and 5 as factors, n should divide the sequence value. So we are done. So to summarize again, we need to find a multiple of n when n is not divisible by 2 or 5, and you know that 2 and 5 makes it 10, which in terms gives the makes it a multiple of any difference between any two terms. And in terms of divisibility, we are considering modular classes, and we need to prove that there is one in the modulo 0 class. But in order to prove that, we need to show that we need to consider all the modulo classes, and there are n modulo classes, and we choose n plus 1 terms from the sequence, and one modulo class is repeated. And by this repetition, we can say that there is a multiple of n in this value, power of 10 into the sequence value, and whenever n does not have factors 2 and 5, we can see that n divides sequence value. So statement 2 and 3 both are correct. Because if it happens for natural numbers, it should also be true for prime numbers as well. Let's move on to question 24. On a sunny day, the shadow of a meter stick. That means the length of the meter stick is 1 meter. Standing upright on a horizontal floor extends to a length of 2 meters. So in these kind of geometric questions, it's good you write a diagram while you are reading. So you have 1 meter, and the shadow extends. So let's say sun is here. Shadow extends to 12 meters. 2 meters. That means you know the angle of the sun. So tan theta equals half. So this is one information. At the same time, shadow of a sphere on the same horizontal floor extends to a distance of 12 meters. Okay, now we know the angle of the sun, but shadow of the sphere extends to a distance of 12 meters. Why? Yeah, the dimension of the sphere is different. So now let's see how does it look like. Sphere is there, sun is there. So can you say like which part of the sphere? So this is the horizontal line. This is the center. So you see, we know that this angle is theta, and sun is here, and since we call this is extended, the sun ray with the highest angle should be a tangent to the sphere. Should be a tangent to the sphere, because after that you don't have any rays tangent to the sphere. Okay. Now what do we have to find? We need to find the radius of the sphere. Now the easy thing to do is, now let's mark the values. This is 12, and according to tan theta, this whole area is 6 because tan theta is half. This is r, and this part will be 6 minus r. If you need to know r, you should have an equation for r. That means r should be present in two expressions, and the two expressions should be equal or something like. We should relate these two expressions. And in order to do that, so you have 6 minus r here. And how about considering the okay, so you can say this is 90 minus theta, and this is theta. So you know this is theta, and you know this is r. And by Pythagorean theorem, this part becomes 6 minus r squared minus r squared root. This part we can write as and another thing, this part is also 12 because tangent lengths are equal, and this part becomes r squared minus 12. Okay, so we can just have 6 minus r squared minus r squared is equals to, okay, Now we have one way for this length. But shall we have another way? We can have another way because this was considering this small triangle. This small triangle. But if we consider the large triangle, we can have this again. Can say this and again we can have another way here. So theta is half. So this should be again r by 2. R by 2. And write 12 plus r by 2 equals so you have 12 here, 6 here. So by Pythagorean theorem, the long diagonal becomes 12 square plus 6 square becomes 6 root 5. So r by 2 equals 6 root 5 minus 12. And r becomes 12 root 5 minus 24. So again just I will recap how we did this. We first found that the sun ray is a tangent to the sphere, and then we already know the angle of the sun ray, and we use that angle in the other triangle as well, and then we use that tan theta of this angle to find that this is r by 2. But we don't need this part can be used, but still it may take long time. So we found this to be r by 2, and we used another formula by using the larger triangle for it to be plus r by 2 equal 6 root 5, and then r can be found. Now question 25. Okay, so this is about so first let's while reading the question, let's draw the diagram. The square ABCD vertices taken counterclockwise. Should be counterclockwise. A B C D. Point B lie on the same plane, not the same square, but the same plane, right? So it can be inside, it can be outside. If the distance from point ABC to point B are respectively simple A, simple B, and simple C. Okay. Let's say, for example, let's say P is here. It's here. This is simple B. This is simple A. This is simple C. And we know that A squared is c square. And what is the maximum distance from point D to point P? So here to here. When you see this, you can see something. Because you are given this equation. And this equation suggests that the point P has some path or a locus. It's not just like one point. You can see it is a continuous set of points, continuous path. So one better option is to find this path. So an easy way to find this path, because if you see the geometry, it may take a long time, but one good method is to use coordinate geometry. So if you use coordinate geometry, and for example, let's look at this. This has 0, 0 and x and y axis. So we can write the expressions for all the lengths. For example, length A. So what is length A actually? We can write length A by Pythagorean theorem. So let's say this is some q point. So A squared equals y squared plus 1 minus x, y minus x, because the actual x coordinate is a minus number, but we have to use the plus number, so the minus number should be multiplied by minus, because the length is a plus number. And similarly, we can write simple b squared equals simply x squared plus y squared. Since it's squared, we don't care about the sign of x and y. And then c can also be found. C squared equals to, can use this triangle, this PBC triangle, 1 plus y, 1 plus y squared plus x squared. Okay, now we have everything in terms of x and y. So when you use the above equation, you can find the locus or the path of point P, because here, like, point P is x comma y. P is x comma y. So let's write a squared minus b squared equals c squared, and y squared cancels out, x square cancels out, 1 minus 2x equals x squared plus y squared plus 2y plus 1, and 1 is cancelled out, 0 equals x plus 2x squared plus 2x, and let's add 1 again, x plus 1 squared plus again y plus 1 squared, and another 1. So this is just completing the squares. I can see that if you inspect correctly, so this is something you should be aware about. So this is the equation of a circle. Root 2 square equals x plus 1 squared plus y plus 1 squared. So this is a circle. So this is an interesting result. This means point P lies on a circle of radius √2 and center -1 or something. Yeah. So -1. So this is a unit square. So this should be mentioned. So all the sides are 1. So what is the point -1? You start with 0, 0, -1. So here. So this is the center. This is the center. And radius is √2. √2 is something greater than 1. So since this is -1, this has 1. √2 can also prove that. So you need to find the maximum distance from D. Maximum distance from D. So you know this is √2. So we'll consider this. CD length is 1, and since the center is -1, this means from here to center you have 1. D to C you have 1. C to the center you have 1. Center to this point you have √2. So this is the maximum distance. Actually, you can also consider the tangent, but you can clearly see that tangent is not lengthy when compared to this distance. So the distance is 1 plus 1 plus √2. Two plus √2, which is the answer. Is the answer C. Let's go back to question 26. Again, sequence of integers, and there are two sequences. Sequence A and sequence B. So sequence A is defined as A equals 2, A plus 1 defined, and B is defined as B is 1, and B is defined in terms of A. Please see that. And then you need to find the ratio of B and A. So best way to do this is, so we need to find the ratio between B and A. So you first make use of the formula between B and A. So you have A plus 1 AN equals 2 AN plus 1 BN. So you are asked BN over AN. So you can find it here. Now you can see each of the ratios is multiplied by 2 to arrive at the next ratio. So you can see that this ratio, so if you can see that Cn equals Bn over An, Cn equals Cn plus 1 equals 2 into Cn. you can say that C, you asked about C 2021. C 2021 equals, so you start from C1, right? So C1, there are uh, from C1 into 2 to the power 2020. So what is C1? B1 or A1? B1 or A1? What is B1? B1 is 1 and A1 is 2. So the answer is 2 to the power 2090. Now question 27. So here it's about, we have a list of powers of 2, and then we need to remove the last digit from each number. And let me show how we're going to remove these numbers. So 2 is removed, 4, 8, 6, 2, 4. So these are removed. And now put them one after the other. So since first 3 numbers are removed, they are not considered, but we can first consider 1, 3, 6, 12, and you can see you develop one long large number. What is the remainder of n when divided by 9? Again, even though we have 2 to the power 2021, we don't have to use brute force. So it's all about using some simplifications, and we ask the remainder of n divided by 9. And if you recall, how do we compute whether a number can be divided by 9 and what is the remainder when divided by 9? We just find the sum of the digits. And if we can find the sum of the digits and remainder of 9 of sum of the digits, we can easily solve this question. And it's easy because it's all about removing last digits. So what we have to do is sum of the digits in the original sequence, original list, minus sum of the digits removed. Then we will arrive at an answer. So sum of the digits in the original list. How can we compute? So the original list is 2 plus something like this. This is a geometric series. We can easily find the summation. We take 2 out. This is 1 plus 2 plus 2 to the power 2020. So you know the formula. A into R n minus 1 over R minus 1. So this is the number. And we can use mod 9 for this. So when you have a product, you can separately compute the modulo of the each term and then multiply them. So when you use it mod 9, 2 into, okay, 2 to the power 2021 is a large number. But when you need to find mod 9, it's good if you can find something a power of 2 which is 1 mod 9 or minus 1 mod 9. So 1 mod 9 I think it's impossible, but you can find minus 1 mod 9 which is 8. So 8 is minus 1 mod 9 and 2 to the power 3 is 8. And 2021, when you have 2021, we need to consider the closest multiple of 3 to 2021, which is 2090. So 2090 can be arranged by using 3 into 673 into 2 to the power 2. Not 9. It happens to be 2 into minus 1 to the power 673. 673 is odd. That is minus 1. Minus 1. 2 to the power 2 is 4. Minus 1, not 9. So minus 5 into 2 is minus 10. Minus 10 mod 9 is also 8. 8 mod 9. One part is done. Now let's see how the sum of the digits removed are calculated. If you observe carefully, the removed digits, if you can also recall the previous similar previous problems, you can find a pattern. 2, 4, 8, 6 are the last digits. Again, you can see 2, 4, 8, 6, and this repeats. So the removed digits repeat according to a pattern. So we just have to find the summation of first 4 and then multiply by how many uh, uh, consecutive terms of 4 are there. So until 2021, you have a multiple of 4 uh, until 2020. So here you can write you have sum of 2020 plus digit of 2 to the power 2021. 2 to the power 2021 last digit, we can find the same rule here. It is can see 2486 and 2 to the power 2021 should be 2. Last digit. Last digit should be 2. So what is the sum of first 2020? You compute the sum of first 4 is 2 plus 4 plus 8 plus 6 into how many sets of 4 are there? 2020 divided by 4. So here you have 20. So 20 is 2 mod 9 when you consider mod 9. 505. 505 is 1 mod 9 plus 2. That means 4 mod 9 and you have, from the previous summation you have 8 mod 9, from second summation you have 4 mod 9, so the answer is 4 mod 9. Answer. Okay, now it's 28th question. So it's about root domination problems. This problem. So need to find the minimum number of rooks so that the whole chessboard is attacked. And here we don't need to worry about how to find the minimum number of rooks, because the result is given. And there is a 7 to 7 chessboard. The minimum number of rooks is 7. And how many ways are there to place 7 rooks on the board? Many ways. The board is dominated. So hint is given. So now let's see how we can handle this. So in order to, so this thing uses inclusion exclusion principle. So we need to find the number of ways. So when it is given that the board is all the free cells are attacked, either all the rows are attacked, all the rows are attacked, or all the columns are attacked. Okay, now let's first compute these two. If all the rows are attacked, that means for each row, like row number 1, row number 2, row number 3, we should have exactly one. We should have exactly one rook for all the rows. And for each of the rows, the rook can be in any cell. So how many cells are there, or how many columns are there? There are 7. So for each row, there are 7 possible columns to make all the rows are attacked. So it should be 7 to the power 7. Similarly, or in symmetry, we can consider all the columns. So for each column, exactly one rook should be there. And for each column, we have to choose the row. The number of ways to choose a row is 7, and it becomes 7 to the power 7. Now, we may get the idea that the answer is 7 to the power 7 plus 7 to the power 7. Thus, what if there are some configurations that are double counted? Let's see. There are some configurations where row and column are unique. Where row and column are unique. So in that case, if all the rows have unique row and column, if they have unique row, that means all the rows are attacked. If they have unique row, that means all the rows are attacked. That means that configuration is counted in all the rows are attacked situation. And when they have unique column, this is also counted by all the columns are attacked situation. That means this configuration with a unique row and column is double counted in this summation. So 2 into 7 to the power 7 summation has duplicates of this configuration. And this configuration, the number of ways for this configuration can be calculated as follows. Like for example, just consider a row. So there are seven different columns the first one can take, but since the column is unique, for the second row, the row can be only set in 6 places because already used column cannot be used. So you can see, since already used columns cannot be used, see 7, 6, 5, 4, 3, 2, 1, which happens to be uh, factorial 7. So the answer is 2 into 7 to the power 7 minus factorial 7. So 2 into 7 to the power 7 is this, minus factorial 7 is this. So this is the answer. Now we are coming to question 29. So this is about running on a circular track, but the area of mathematics is rational and irrational numbers. So the track is divided into equal segments. So the the key points are the perimeter. The perimeter is 1 meter, and there are track is divided into equal segments like 2022, 2021 number of segments. That means one segment, the length of one segment is 1 over 2022, 2021, and starts from 1, 2, 3, and so on. Now let's see what are the statements. And his speed is v meters per second. So if v is 1 over 2020, v is 1 over 2020, is it possible that Nipuna be strictly inside segment number 1 of the track at some observation? Let's see others as well, because the statements are similar. For different v values, we need to see whether Nipuna is strictly inside one segment. So the meaning of strictly inside is Nipuna is not on the boundaries. He is inside this. Inside this. That means it should be a number. Like it should be something like 1 over 2020 to power 2021. So these are the boundaries, right? This can be a boundary. Integer into its length. This is the length of one segment, and the length that is towards the next segment is m plus 1. So when like v into number of observations, v into number of observations, let's say vt, is between the two consecutive multiples of the segment size. That means he is inside the segment. He's strictly inside the segment because this is not less than or equal. This is less than. Yeah. So that means, like for example, let's see. So when it is 1 over 2020, so he goes somewhere, and then 2 over 2020 goes somewhere. So what we need to prove is whether he becomes uh, strictly inside these specified segments. So let's start the first statement. If v equals 1 over 2020, is it possible that Nipuna be strictly inside segment number 1? So this is segment number 1, and he's going this way. Right? He's going this way. So let's see. So this is 1 over 2021, and v is greater than 1 over 2021. So V is 1 over 2020, and we have 1 over 20 to the power 2021. And suppose uh, we have we choose the segment number, choose segment number, choose this segment. The length towards this segment is 2020. You can see that the length towards the segment number 2020 to the power 2020 is 1 over 2020. Can you see 1 over 2020 goes to the segment number, I mean the last segment, boundary of the last segment, boundary of the last segment. So that is from the first observation. First observation, V is 1 over 2020, and 1 over 2020 is the last segment boundary, because this is the last segment. Choose this segment which is the last. From the last segment, when we calculate the length is 1 over 2020. So when he runs in 1 over 2020 speed, he can be first observed at the last, and you can see at the second time he can be observed here, because now it's a new starting point. So you can see that he can be observed in all the boundary points, but he can never be observed inside a segment. He can be only observed on the boundary points. That means the first statement is false. Right. Hope this is clear. Now I'm going to consider 2 and 3 under the same rule, because both speeds are irrational. Irrational means that cannot be represented as a ratio of two integers. Okay. Now let's see whether when it is irrational, whether it is possible to be on the boundaries. It is possible to be on the boundaries. So let's check it. So let's say the V is 2020 square root, and let's say into K. So this is the kth observation. So length towards kth observation, and let's say we consider the modulo 1. This modulo 1 is why it is modulo 1. When you divide something by 1, the remainder is the fractional part or the decimal part of a number. You can say it's modulo 1. So if we don't consider modulo 1, just see like this extended line. So 1 over 2020 into K should be equal to so this is the length of one segment into some number, right? It should happen if assume 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 observation is made on boundaries. So if an observation is made on boundaries, that means, so this is a general observation, kth observation, and this is the mth boundary. So if kth observation is done on mth boundary, that means 1 over equal m over k into 1 over 2020, 2021, which makes this is rational, which is a contradiction. If you remember the proof of root 2 being irrational, so it's similar. So this is an irrational number which can be shown as a rational number, which is a contradiction. That means no observation can be made on boundaries when V is irrational. So that means the result is, final result is, the intermediate result is when P is irrational, no observation on boundaries. Okay, now one fact is clear. Now let's see whether there is an observation, whether we can find an observation on segment number 1 or segment number 22. For that, we need to prove that there is an observation within a segment. Within a segment, there is an observation which can be shifted to segment number 1 or segment number 2022. So now we have proven that we can find it on some segment. Strictly, because we know that now it cannot be observed on boundaries. So there are many segments, and we know that it can be found on some segment. But we don't know whether it's segment number 1 or segment number 2022. So since we know that there's no observation on boundaries, the next step we have to prove is there should be an observation on the first segment. But how can we say that? Like it's very difficult. So maybe like it can be easy to say about first segment, but when it comes to 2022 segment, it's very difficult. We need to do many calculations, but we can use our intuition to prove this. So if you remember the number sequence that we considered in a previous question, what did we do to say that there is a multiple of a number? We considered the difference between two numbers, right? We can do the same logic. So we are trying to see that there's a multiple, or something belongs to the first segment. So we take any segment and use that to prove that there is something in the first segment. So here also we are using pigeonhole principle. So let's say that there are we consider 2020 to 2021 plus 1 observations. if consider that much of observations we have, we can find a segment with two observations. So let's say that means into K1 also falls in one segment. Let's say this is the segment, and K2 also falls in the same segment. Now let's consider the difference. So you consider an arbitrary segment and use the difference to locate it to the segment 1. So without loss of generality, K2 greater than K1. You can see that the difference corresponds to another observation. Another observation. Another observation in the first segment. Segment 1. Okay. Now statement 2 is correct. Now what about statement 3? Statement 3. So it says there it is strictly inside segment number 2022. Now if you remember how we concluded that Nipuna is not inside number 1 track. So we found that he starts here, and in the first observation he is at the last boundary, and next observation he is at the next boundary, and he can go on and on, but on the boundaries. So we can see a similar representation. So now we have proven that it can be strictly inside segment 1. Segment 1, and the corresponding number is K2 minus K1. So let's consider it as K star. Okay. So what happens when it becomes 2K star? So let's say when it's 2K star, so for K star it is something this. When it becomes 2K star, it goes like this. Two K star is also and can you see that this can take you from within one segment. Now let's say you are there at 2021 segment, and definitely you land at 2021 segment. Like let's say any segment. If you land before one such segment, if you land, let's say the last segment that you land on, and after that you cannot jump this segment because you already know that the difference between two segments is less than the segment size. So you must go inside particular segment. So let me explain it again. You say that you are not going on some chosen segment, we can disprove it because in the segment before, let's consider the last number after the segment. Um, and it's a linear number. So after this number, uh, if you miss this segment, the next number should be inside the other segment. But the difference between these two is greater than the segment size, which cannot happen. So that means it must be the case that a segment, like any segment, is not left out with observations. Because if in any case one segment is left out, there are two observations which are far away, which is not the case, because we have proven that two observations should be inside the segment. The distance between two observations should be less than 1 over 2020 to the power 2021. That means all the segments are full of observations. That means the track number 1 has an observation, also track number 2022 also has an observation. So both are correct. So coming back, in the first case, 1 over 2020 was a rational number, and 1 over 2020 could be represented as a multiple of the segment size. That means 1 over 22 lands on a boundary, and then we can show that after each observation it lands on a different boundary, which shows that it can never be strictly inside a segment. And secondly, we have proven that irrational jumps will not end up on boundaries, and it should be strictly inside some cell or some segment. And if it can be inside some segment, we use pigeonhole principle to show that there can be a segment with at least two observations, and we use those two observations to show that there should be one observation within the segment 1. And then we used logic to show that mm, all the segments should have such observations, because if you left out a segment, uh, there are two observations within unreasonable distance. So this is the explanation. So let us go to the final question. So it's about a rectangular wall with k rows of tiles. So you have k rows, and in the first row, rows are numbered from bottom to top. So row 1, 2 to the power k minus 1, and then 2 to the power k minus 2, and so on, and then 2 to the power 0 on the top. So 2 to the power k minus 1, yes. And there are some rules. So you have only red, green, and blue to color them. So if you have two, and the color of the tile above is determined by the colors of the tiles below, which are adjacent. So if you have same color, the high level will be drawn in same color, and if you have different, like for example here you have green, so this should be green color because it's same. And when you have different colors, the remaining color, for example we have red and blue, so the remaining color is green. Here also we have red and green, the remaining color is blue. So that's how we do the coloring. Now let's see the statements. If k equals 2021, there is color in the first row, where 2 to the power 2019 tiles are red, to the power 2029 tiles are blue. And you can see that all the statements are written for k equals 2021. So for the first statement, it says that there exists a coloring. There exists a coloring, so you need to choose just one coloring such that this condition is satisfied. So ends up color green. So let's say you have all of them, the first half red and the second half green. Sorry, second half blue. First half red, 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 red. Second half blue. You can see that up to the last point, all the colors in the first half becomes red, and all the colors in the second half becomes blue. Finally, on the last cell, it becomes green. So there exists a coloring in the first row such that top one becomes green. First one is correct. But when it comes to the second one and third one, it's not just there exists, but all the colorings of equal number of red and blue first row ends up in green. So that is the first statement. And second statement is when there are 21 red tiles and 22 to the power 2020 minus 2021 blue, then also it ends up in color green. So when you get this kind of question, chances are high that there is a general result, and general result in a way that there is something that is invariant, because here we say about like any coloring. Like in the second case, it is for all colorings, where this all are red and like half are red and half are blue. And for the third statement also, there are several number of colorings. So we need to find an invariant. That means for any of those different configurations, there should be something that does not change. So here, since we have three colors, let us use modular arithmetic, because use this because it can be invariant, because the order, like for different orders, modulo sum does not change. For different orderings in first row. And that means we can use the modulo sum to reason about the color configurations, and we can also use the modulo sum to derive the color configurations in the above rows. So let's use red equals 0, blue equals 1, and green equals 2. Since we have 3 colors, we use all the modular classes of 3. And it's not very difficult to figure out that the modular summations. So let's say we have modular summation of k in the first row. Why we need this? We need to derive the modular summation in the topmost layer. So if we derive the modular summation of topmost layer, we can define we can determine what is the color in the topmost layer. So what we are going to do is we start with the modular sum in the first row, which does not change with different orderings, and we use that to infer the modular sum of each layer, and finally infer the modulo sum or modulo value of the topmost row. So let's see for the first case. If the modular sum for the first case is k, now we are going to have a parametric equation. If first row is k, what is the second row? Can you see that? If first row is k, let's take two scenarios. Let's say if we have similar cells. Let's say red. If red is there, 0 plus 0, we will have another red. It's again 0. And let's say blue. 1 plus 1, we will have another 1. But actually 1 plus 1 is 2. But we have 1. And let's say green. We have 2 plus 2 equals 4. In modulo it's 1. And we have 2. Can you see a relationship? When blue, can you see a relationship? These all add to 0 mod 3, right? So all add to 0 mod 3. I mean the initial sum in the first row 1 and row 2. Row 1 is 0, row 2 is 0. Row 1 is 2, row 2 is 1. Row 1 is 1, row 2 is 2. You can see these sum up to 0 mod 3. That means if row 1 has k mod 3, can you see that? Row 1 is k mod 3. Row 2 is 3 minus k mod 3. Right. So you can see that each even, so this alternates. So what we have to do is, for the second statement, find k. So 22 to the power 219 red, 2 to the power 219 blue. Number of red is 0, so that is 0 mod 3. For B we have 1 mod 3. That means 1 into 2 to the power 2019. So 2 to the power 2019 is minus 1 mod 3 to the power 2019 is minus 1. It's minus 1. So in other words, 2 mod 3. So that means first row corresponding to the second statement, row 1 is 2 mod 3. Row 2 is 1 mod 3 and it alternates. And how many rows are there? 20, 21. Odd number of rows. All the odd rows have 2 mod 3. So row 2021 also have 2 mod 3. 2 mod 3 means green. So this is true. So can you see like how we approach this? So here we have like for all coloring, first row is green. That means for all coloring, the color of the first row is not changed. So we need to find something that does not change for all colorings. So we have chosen the modulo value because modulo value does not change for different orders. And we have proven that by using that modulo value, we can infer the modulo values in the top levels, and then finally we can infer the modulo value in the topmost level, which gives that it is always green. Now let's see the third statement. 2021 red. Now let's see what's the modulo value. So R, so red is 1 mod 3. So red is 0 mod 3. So 2021 red means 0 mod 3, 0. And 2 to the power 2020 is minus 1 into 2 to the power 2019 into 2 minus 2021 into 1. So here it's minus 1 to the power 2090. So this is again minus 1 into 2 minus 2021 is 2 mod 3 minus 2 minus 2 minus 4 equals 2 mod 3. So you can see that in this case also first row is 2 mod 3. In the case before also first row is 2 mod 3. Can eventually prove that the topmost row becomes green. You can see that even though this is shown as a complex question, we can use an invariant which does not change for different ordering to prove the topmost value or the topmost color. So this ends the discussion for 30 questions of 2021 SLMC 13 paper. Hope you got something out of it. So please follow this several times if it's difficult to understand, and please do these questions and please think about these questions, and you have previous past papers as well, so try those as well, because you should improve your observation skills and critical thinking skills. So you should observe and you should use critical thinking to deduce from observations. And you should also strategize your time. You should select which questions you're going to answer, which questions you're going to leave out. And because it's better if you can have a good grade. And again, at the end of the day, it's all about you learning. When you learn to think critically, that will be useful for your day-to-day life and to excel in your other subjects as well. So good luck. Wish you good luck for you in SLMC 2022. Thank you. I am 𝐷𝐿𝐿𝐵 Fernando from Sri Lanka Olympiad Mathematics Foundation. So I was 2 times IMO participants, 2009 and 2008. So I'm very glad to share my experience with you. Hope this helped. Thank you and good luck.